Thank you. So hi everyone, my name is Antoine Sherlock and I'm a PhD student from the Universidad Rey Juan Carlos. And today I'll talk about high order elasticity interpolants for microstructure simulation. So microstructures are a powerful way of controlling mesoscale behavior under limited material choices. Each microstructure can give a specific elasticity response on a mesoscale level. So consider you want to give an arbitrary elastic behavior to a batch of 3D printed material. You can do it by choosing the right microstructure pattern. Same thing with 3D printed structures. You can give it a desired elasticity response with the right microstructure distribution. And if you want to give a special shape to a dress or a stand, you can also use microstructures. However, simulating large objects with at microscale level is computationally costly, so modeling their behavior on a mesoscale level appears a better strategy. Modeling mesoscale behavior of a microstructure is challenging as it shows nonlinear responses. On the first image, you can see anisotropy response, and other phenomena like buckling or oxidic response are also common in microstructures. In this work, we'll present a strategy to modelize accurately their mesoscale behavior. Okay, so consider we have a section of microstructure, and we want to find an equivalent material or a constitutive model that behaves as the fine microstructure does. So this process is called homogenization, and research in this direction is extensive. So homogenization is a common strategy to design mesoscale material models that accurately represent the aggregate microscale behavior. Miguel et al. Developed a method to homogenize real-world hyperelastic heterogeneous objects. So what they do, they measure force deformation relations of the object at different sample points. Then they feed the collected data to an energy-based model for elasticity. Their parameterization aims to replicate the nonlinear behavior of the whole object. So this strategy is interesting, but the energy model is not designed to interpolate stress values by construction. And the stress is the most relevant component of a constitutive model. We simulate elasticity by reaching equilibrium, which means finding a configuration where the sum of forces equals 0. Also, another cons is that they enforce convexity by projecting the stiffness of their parameterized energy, which deteriorates the fitting. Wang et al. Proposed a similar data-driven method to accurately animate objects from real-world measures. They designed a constitutive model based on strain-stress interpolation with radial basis functions. However, this method is not conservative, and they don't take into account the convexity of the potential energy, which is critical for the convergence of the model. Yarn level simulation are expensive to compute, and Sperl et al. Proposed a homogenization method to capture simulated yarn behavior and replicate it in thin shell simulations. They simulate relevant deformation of periodic patterns on yarn level and collect the energy values. Then they use an energy-based elasticity as described previously in the Miguel's paper. However, this method suffers the same limitation. It does not interpolate the stress values, and convexity is also complex to enforce. Yesterday, Jong-Yoon presented a way to locally homogenize heterogeneous material called coarsening. So this method allows fast simulation of objects with high resolution heterogeneity. This idea of coarsening is to estimate coarse to find behavior of relevant metrics. In this case, they use matrix shape functions to evaluate fine displacement given coarse displacements. However, this method is not designed to model nonlinear elasticity by construction. So in our work, we want to design a mesoscale elasticity able to capture the complex behavior of microstructures while being conservative. So in the first place, I will present a parameterization of the elastic energy that defines the mesoscale material constitutive model. Secondly, I will show how to generate representative data of our microstructure. And finally, I will explain how to estimate the parameters of our parameterized energy. So let's start with the energy parameterization. When designing elastic materials, we want to preserve strain stress response and strain stiffness relation. Then energy conservation is a fundamental property of elasticity. So our parameterization needs to be conservative by construction. Finally, we need to ensure that the parameterized energy doesn't generate forces at rest state. We define our parametric function such that it interpolates given values of energy derivatives, which are the stress and the stiffness. To do so, we developed high-order radial basis function that allow us to interpolate any high-order derivatives. Now let's give a closer look to it. So let's consider a 1D green strain domain. Each deformation of a microstructure generates a stress value. We simulate various deformations and populate the strain domain with all the corresponding stresses. Now our challenge is to find a good interpolation that will be the constitutive model of our homogenized material. To design our energy models, we look at radial basis functions. The approach appears simple. If you want to interpolate a scalar field, such as the energy, we just design RBF interpolants and we need to estimate their weights. However, we're interested in interpolating the derivatives of the energy, such as forces. Well, we could apply RBFs to interpolate vector fields, and this time we just estimate the vector coefficients. Unfortunately, this approach is not conservative. In other words, the resulting vector field is not the gradient of a scalar field, the energy. There is actually another way to interpolate vector fields using RBFs, which relies on matrix-valued RBFs. We build the matrix of RBF functions using the Hessian of a scalar RBF function. And the resulting vector field is conservative by construction. And the energy function can be obtained as shown on the slide, the 5 there. So in our paper, we show that RBF interpolants can be extended to higher order derivatives. This will help us interpolate the Hessian of the energy. Our first result is that we express the energy in a more convenient way without RBF derivatives. We show that this expression is equivalent to the one before. It just requires a different choice of coefficients. Here you can see some of the interpolants produced by this energy model. We obtain local control on the gradients of the energy, the forces. Our second result is that we extend the interpolants to higher order derivatives. Here we have the energy expression for Hessian interpolation. And here you see some of the resulting interpolants. This time we obtain local control on the Hessian of the energy. Finally, our mesoscale energy parameterization is composed with the first and second order RBF interpolant to fit the stress and stiffness data. Then we add a stress offset to easily enforce zero stress at rest state and the stiffness offset to easily fit the average stiffness. So in this way, the RBF interpolants act as correction with respect to the offset terms. Now we have defined how to parameterize the energy. Let's see how we generate data representative of the mesoscale microstructure behavior. We inspire our data generation from Spiral 2020. We simulate 2D microstructures under planar deformations with periodic boundary conditions. This approach makes the mesoscale strain uniform and enables easy transfer of the training data from microstructure simulation to mesoscale. We model a repeatable tile of microstructure at high resolution using a finite element mesh. We stretch it along various amplitudes and direction and search for an orthogonal stretch that produces zero stress. So it looks like this. Here you can see how we apply the stretches. Each deformation generates a mesoscale stress and stiffness, which corresponds to the dots populating the strain domain. On the left, each dot shows the norm of the stress, and on the right, we have the norm of the stiffness. Now we have collected the stress and stiffness data. Let's see how to estimate the parameters of our parameterized energy. We start by optimizing the location of our RBF centers with a k-mean clustering algorithm. In our paper, we designed the objective function that minimizes the error between the data and our parameterization. We find the parameters solving the optimization while sweeping the radius of the RBF functions and pick the best result. And we repeat the previous steps, adding RBF each time until we reach desired precision. So you can see in this video the accuracy of our fitting. On the top, the target stress and the stress from our parameterized energy. On the bottom, the target stiffness and the fitted stiffness. We compared the fine periodic simulation with our coarse model. On the left is the high resolution simulation with the purple checkerboard representing its mesoscale behavior. On the right is our homogenized model. We realized this previous test on a library of 11 microstructures. The last column of the table shows the accuracy of our homogenization on the previous test. You can see that for most of them, the coarse simulation has less than 10% error compared to the fine simulation. Finally, we evaluated our model on non-uniform strain deformations. We compared the high-resolution simulation to a coarse FEM model using our fitted energies. The high-resolution microstructure uses 4,000 elements, while the coarse model only uses 36. So to conclude, we have presented a new tool to interpolate stress and stiffness. It allows good interpolation of nonlinear behaviors and conservativeness. We showed our material model can be used for microstructure simulation as periodic simulation and regulatory simulation. Our work can open interesting avenue for future work. It is extensible to 3D simulation, and it can be highly improved by optimizing the meta parameters. And that's all. Thank you.
Great. Questions for Antoine? Hey, we got one here.
Antoine, really nice results. Thanks for the nice presentation. A question about the visual appearance patches. Are you also learning this as part of the course model, or is it just the elastic stress?
So yeah, so you mean on the patch like the non-uniform strain, what I showed?
Yeah.
Yeah. So no, what we learn is just from we learn the data we collected from the periodic simulation, and we use it in with a non-uniform strains.
But do you think it could be possible to start these nice patterns that you're getting as well, or the visual pattern of the microstructure?
I think maybe coupling with coarsening, so you can like kind of learn what's going on the fine level. I think so. Yeah, there would be a way to do that.
And do you think there's a way to extend this to take into account the contact lens?
Yeah, I think so. It's just like the point of the interpolation is like to learn the nonlinearities, and contact is a nonlinearity. So
should work. Because I think you assume that all contacts are active.
Sorry?
All contacts are active in the patch. Like,
yeah. So in this work, we didn't take into account the contacts, but we could.
Right. Thank you. That's working.
Oh yeah, super interesting work. You showed that table with all the errors for different patterns that you tested and looking at coarsening things. Have you investigated whether there's any structure or pattern to the error? I know there's a lot of papers to try to, like learn a model for the error or something, some machine learning thing, and like, project that out. So I don't know, have you looked at any kind of, or thought about any techniques to drive all those coarsening errors down?
No, we didn't include any machine learning strategies in our work, but yeah, maybe it should be some future work.
Cool. 2 questions.
Thanks for the nice talk. So my question is, do you foresee any problems when extending this to 3D, especially with regards to like combinatorial explosion or data generation? And or what actually happens when you're outside of this learn stress strain relationship?
So yeah, okay. So in 3D, yeah, you're gonna have like more data to generate, but I think it's doable. And when you get out of the, when you extrapolate, when you're out of the training data, so that's the point of having interpolants and the offset. So the offset basically, I don't know if I can show you the slide. So the offset, yeah. So the offset is basically just a Saint-Venant Kirchhoff energy. And the interpolants are actually just correction for nonlinearities. So when you're really out of the training data, it's just still going to behave as any like Saint-Venant material.
So just fall back to
Yeah, it's not going to be super accurate, but it's not going to crash either.
Okay.
Great. I think there's maybe one more question back there.
So thank you for the great talk. A lot of this work focuses on periodic tilings, and maybe my question is a bit naive, but how does this extend the non-periodic tilings or structures with a very large spatial period?
Well, I guess that's some of my future work. So, yeah, we don't really know yet, but when you have like, there's a point of homogenization when you identify really like periodic tiles, you can like say that this region, you can use this strategy for this particular region. And what's interesting is like maybe learning what happens when 2 regions of 2 patches of periodic microstructure get in touch, like get contact. So by times together. So
Thank you.
All right. Great work again. A lot of interesting follow-up directions. Let's thank our speaker one more time.